All right. So, couple of things. I've been so wishy-washy. I couldn't figure out the flow of the material. And then finally, I think it was just yesterday or maybe the day before maybe, where I said, you know what, I'm just going to pick some test dates and we'll see what happens around that. Okay, so first thing I want to mention is test number 1 is on October 16th. Let's see if I can get it. Whoa, one screen. Who says you can't do it all in one screen? Whoops. Okay, that was probably only weird for me. Oh. Crop. Hey. Yeah, I wanted to put it in here, but so then things are just not working for me today. Oh my gosh. Okay, that's okay. October 16th, test number 1. Now I'm hoping that it's going to be on chapters 1, 2, 3, and exponents and logs, which is from a different textbook, which I've posted already. Okay, and so that's on a Monday. We might not get through exponents and logs by that day because we've got all these holiday Mondays that we're working with. So things will have to be a little bit different. So next week we're doing logic in chapter 3 and then same setup examples on the Friday. But then I posted this chapter 4 from Lipman and Rasmussen, which is just a pre-calculus textbook, but we need to talk about exponents and logs, and that's a good place to grab it from. And so we'll use that as our chapter 4. It works out so beautifully because we're skipping chapter 4 in our textbook, but then I grabbed a different chapter 4. It's perfect. It was meant to be. And then, so that's what I'm hoping, but if we don't get through exponents and logs, then that's fine. It won't be on the test, obviously, so I'll adjust it as we go. But yeah, these holiday Mondays, when we have a Monday, Friday section, it's not really working out that well for me, but you don't need to sweat it. Okay. So the exponents and logs, I spread them out over those 2 weeks, but it's only 2 classes. And then test 1's on that Monday. Okay. I thought it would be nice to have the test on a Monday instead of the Friday, but test 2 is on a Friday. Sorry. But I did have someone email me and say, oh, okay, well, that's fine, because then we have more time to study. So you're welcome. It's not the Sunday, or sorry, it's not the Sunday. Oh my gosh, I need to go home. It's not the Friday before the long weekend, it's the Friday after. So then party's over anyways, and we can just get to work, right? So pretty ambitious, chapter 5, 6, 7, 8, and 9. But chapter 5, we only do one section, and it really only introduces matrices, and then we use them in chapter 6. So it's not as bad as it looks. Yeah. So those are the 2 test dates. So test number 1 is on October 16th, so Monday, October 16th, and I guess I could write test number 2 is on Friday, November 17th. And I'm really sorry. But I couldn't get it to work. I couldn't. Any other way. I'm sorry. You do have to come to in class. Yeah. Oh, thank you. That's my job to freak out. Okay, phew. I am. Say that all over again. Well, I haven't said much, have I? Just been blabbing. Good thing I am. Thank you. Okay, you have to come to class. In class test only. Remember, I don't give makeup tests, but I'm willing to pretend like you didn't show up to one and shift that weight to the final exam if you do better on the final exam on one of them. So you're better off just writing the tests, or if you have something come up, you're sick or whatever, you can't come to the test, then I'll just shift it to the final, but I'll only do that for one of the tests. Okay, so choose wisely, or better yet, do both, and then play the field, so to speak. Right. If your final's better, then one of those, I'll shift it over. What else? What else? I posted assignment 2, which is on chapter 2. Now there are a few questions in there that I want to cover today because we didn't quite finish section 2.4. So if there were some questions in there, I mean, you could brute force it and answer them, but I'm going to give you a little shortcut. Okay. And so I posted the exercise solutions, but what do I want to do now? In terms of review, let's just do some brief review. Having a hard time remembering what's from what week, but we talked about permutations. Right. Permutations are when order matters, right? And so here, order matters for things, for arrangements of letters and things like that. Okay. And then we also introduced combinations where order doesn't matter. In terms of notation, the permutations we have n, oops, so Pn, oh, it's lagging, K, right? The number of permutations of size K that I could form out of n elements. Now, I guess I should write that out. Ha. And maybe I'll bump this down here because I can. The number of permutations of size K from n elements. Whereas combinations, we use this function n choose K, right? Which is also, or if you prefer, a capital C bracket n comma K, which is the number of ways that we can choose K elements out of n elements. The number of, I guess, combinations, but I think it's more clear if I say the number of ways we can choose k elements from n elements, where order doesn't matter, right? That's a nice end to the review. I've got the new page. It was almost like I planned it. I didn't, but almost. So we did start this section, but I just want to do a little recap, get us up to speed. Okay. So here I did highlight order is important in permutations and order is not important in combinations. In terms of reading questions and deciding is order important or is order not important, right? That's going to be your first step in deciding if it's going to be a choose function or a permutation function, right? And so that's your first thing that you're going to do. And all right. Did we do this example? I feel like we skipped it. Maybe we did. Maybe we didn't. We're doing it pseudo again. So if we have a set of A, B, C, D, okay, how many different ways are there to permute 3 letters from this set? Okay. And so now each permutation, right, cat is different from act. Same letters, but they're different, right? So those would be the permutations. And so how we calculate that is P of 4 and 3. Now on your calculator, the only one I have on here, and my apologies in advance, is this business calculator, which has ads. So we'll see if we have to put up with any ads, but
Shouldn't your tablet come with calculator from the stop?
It does, but it doesn't, I don't think it's very good. I don't like it. And I have the Desmos calculator, and I've got so many calculators on here, it's insane. But this one I know has the choose function. So here, if I press the plus, you'll see that that's where the NCR button is, and then there's the NPR button. Typically, how any calculator works is you have 5, and then you have to hit second NCR, for example, choose 3. Now that's a bad answer. It doesn't like it. I think I did something weird. 5, choose 3, 10. There are 10 ways to choose 3 elements from 5. Okay. I don't know what that negative was. It didn't, it's mad at me, I think. Okay. And so you can use your calculator to calculate these functions. Any calculator will do. And what I did in the solutions, now I can, don't get seasick. When I twist it around, what I did in the solutions is anytime that there was kind of a combination or permutation, I wrote out what you should be getting so you can check it, right? Otherwise, it's hard to know if you're doing it right. Okay, so we can use the factorial formula, but I'm going to encourage you to just use your calculator. If you have values, then just use your calculator and find that value, right? What if we wanted to know how many ways can we select a set of 3 letters from A, B, C, D? Okay. And this is the one that I said, okay, we did that last week, right, as one of the exercises, and we brute forced it. We just listed all the possible combinations, eliminated ones with duplicate numbers because we only count things once in a set, and things like that, and order doesn't matter. And so wouldn't this have been nice to know last week, right? Before we had to brute force it all. But what we end up with is there are only ABC, ABD, ACD, and BCD are the only 3-letter combinations that are possible. And order doesn't matter, right? So ABC, that's covering ACB, BAC, right? All that kind of stuff. So how we find that is we're just choosing 3 elements from 4. Order doesn't matter, right? So 4, choose 3 is what on our calculator? Should be 4, right? 1, 2, 3, 4. So I'm gonna do 4, choose 3, but I'm gonna use the Desmos calculator because it's a little bit nicer. And I think I have a function. NCR is down here on the bottom. Sorry, I don't have the pointer on anywhere else but the notes. So if I use the NCR function and I want to choose from 4, 3, then I get 4, which matches the answer that we found. By brute forcing it, we actually listed all the numbers to figure it out, but we could have just done this and probably map back and figured out, okay, well, if there's only 4 that I'm finding, I can find those. Okay. So here, all right. 4, choose 3 is equal to 4, as we've seen. Okay. So here, these are the combinations and these are the permutations, just to emphasize that for one, order matters, and for the other, it doesn't. Well, okay. There's a formula and it involves factorials again, but like I said, just use your calculator, right? Just know how to find these, choose functions and the permutations on your calculator, and then you're good to go, right? Or if you are stuck with a variable, then I would just leave it as, 4, choose K or something, right? If you don't have K. Did you hear that voice? It was way too young to be here.
It was very smart.
They're here for class. I love seeing young kids in the hallway. I think it's so cute and so funny because they're just here with their parents, obviously. But flipping a coin. We said, okay, well, if I'm flipping a coin 5 times, one of the outcome options is I flip a head, I flip a head, I flip a head, I flip a tail, I flip a tail, right? Or I could flip a head, flip a tail, flip a head, flip a head, flip a tail. Regardless, I have flipped 3 heads, right? So here, 3 heads and 2 tails. There are many ways that I could rearrange these combinations, right? And so there are many combinations. And so what we use is we say, okay, well, to figure out how many ways that I could rearrange, and we have to stick with one of these, it doesn't matter which one, right? Rearrange 3 heads in 5 flips. That implies that there were 2 tails, right? So you only need to focus on one side, I guess. And so how many ways can 3 heads be obtained? Okay. 5, choose 3. We saw it on the calculator. First I got -10, that doesn't make sense. +10 makes sense though. And that's what we get here, right? And so here we're just saying, okay, well, I don't care where the heads were, right? They didn't have to be first. They didn't have to be every other one or anything like that. If we add conditions like that, then we're back to kind of a permutation style, right? But here we just said, how many ways can 3 heads be obtained, right? So now we're just choosing 3 out of the 5, and how many ways can I do that? Okay. we can extend it past just 3 heads. What if I want to know, okay, well, how many ways in total can I see all these outcomes? Okay. And so then we say, okay, well, I could have 5 heads, or I could have 4 heads, or I could have 3 heads. Notice how I'm saying or, right? Whenever we're saying or, we're going to be adding later. And whenever we end up kind of saying and naturally, then we're multiplying. So that's something to keep in mind. So 5 or 4 or 3 or 2 or 1 or 0. That's the one that's the easiest to forget about. Whoops, oh, weird. Right, but I'm going to write a note here. Don't forget about 0 heads. That can happen. What does that mean? It means it's all tails, right? Just like we said we could have 5 heads, I could have 5 tails, meaning 0 heads, right? And so that's the one that always slips my mind. And then I go and, oh, that's okay, that's the wrong answer. Oh, I forgot the 0. So don't forget the 0 option. Okay. So we can figure out how many different combinations I have, right? Flipping just 5 times by adding these all up, right? 5 heads or 4 or 3 or 2 or 1 or 0. And I'll just write or here. And we get 32 different ways that we can arrange it. Okay. The easier way to solve this is our trusty, or my trusty 1, 2, 3, 4, 5. Sneak it on there, right? 5 coin flips. Each flip I have how many options? I have 2, 2, 2, 2, 2 options. Multiplying through here, I get 2 to the power of 5, which is 32 again, right? So I'd say my go-to move is probably like this. If I had to figure out how many different ways or how many different outcomes can I have, right? But this gets you to the same value, right? So there's nothing wrong with it, but it's your job to figure out which way you kind of go to most naturally. Okay. Okay. I think that's where we ended last day, but a little bit of a recap can't hurt, right? So this is, sometimes we call the choose function the binomial coefficient. And if I asked you, okay, how many ways can I have 0 heads in 5 coin flips? There's only one way that I can have that happen, right? If it's 0 heads, it has to be tail, 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 tail. Tail? Lost track, right? How many ways can I have 5 heads? Only one again, right? Has to be heads, 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 heads. Right? And so those outside, you'll see why I'm saying outside choose functions in like 1 minute. They're always just going to be 1. So if I'm choosing 0 or if I'm choosing n, those are going to be just, there's only one way of doing both of those. In fact, the useful part, or how we're going to use the binomial theorem, is kind of as a shortcut for expanding things like x plus y to the power of n. That's useful if you have x plus y even to the power of 6, what would you have to do? And this is something basic like x plus y. You would have to do x plus y to the power of 6 is x plus y times x plus y times x plus y times x plus y, 4, oh boy, x plus y, x plus y. And then what would you have to do if you had to expand this thing? Oh boy, you have to FOIL it one at a time. Then FOIL that onto here, and so on and so forth. That's going to take forever. And that's just the power of 6, right? So how we're going to use this is with this, do we call it? I think we call it, okay, yeah, we do call it Pascal's triangle. I wasn't going to call it that if we didn't call it that in the notes. Okay, so this is Pascal's triangle. Now, what happens is if you were to expand out x plus y to the power of n, if we let n be 0, anything to the power of 0 is 1, right? So that's where we start. If we let n be 1, well, that's just x plus y, right? So here, so far we're doing pretty good, right? What if I let n be 2, then I get x squared plus 2xy plus y squared, right? If you expand it out. And then if you multiply it by x plus y again, you expand it out. And what I want you to focus on are these coefficients. Here, 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 here. Here, 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 here. Here, 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 here. This is why we call it the binomial coefficient. That's not obvious to me, Emily. That's all right. What's going on? Why did I call those extreme choose functions? If I choose 0, then I have a coefficient of 1, right? And so here, these are all 1. And if I choose all of them, all of the n, right? So 2 choose 2 is 1, 3 choose 3 is 1, 4 choose 4 is 1, 5 choose 5 is 1. So what's happening in between here? Well, it's right here, I guess, but I'll write it out just to emphasize. I'll focus on this bottom row here. 5 choose 0 times x to the power of 5. Then 5 choose 1 times x to the power of 4, y to the power of 1. Okay. Notice that the total power is still 5, but what's going to happen is it's being spread out across your x's and y's, and it is being spread out methodically. Right, so here you decrease the x by 1, which means y gains 1. And then here you decrease the x by 1 again, which means the y gains another one again. Okay. And then you keep going until there is no power on the x. X to the power of 0 is what? 1, right? So 1 times y to the power of 5 is technically what it says here, right? So just note this relationship of how the power of x is decreasing, but that means the power of y is increasing as you move along. And then these binomial coefficients here, 5 choose 2 is 10. 5 choose 3 is 10. Why are they the same? It would be the same as saying, okay, well, 2 tails means what? If I flip a coin 5 times, 2 tails means I have 3 heads, right? 3 heads means I have 2 tails. And so that's why these two are the same, right? There's only two outcomes. And so that's why the number of combinations is the same. And then same idea, 5 choose 4, right? Either one, if you think of it in terms of successes and failures, right? Either one success, which means 4 failures, or 4 successes and 1 failure. Same but different. And then 5 choose 5. Don't worry. We're going to make this more general than just to the power of 5. Haha, I know you were worried. Okay, but that triangle has a lot of fun properties. Let's talk about Pascal's triangle again. And when I took my first computer science class, which I had to withdraw from because I was doing that terribly, it was a strategic decision. And what the funniest part is, my dad's a software engineer. And so I'd go home on the weekends, get help. And finally he looked at me and said, Emily, I don't think that you're a programmer. Okay, Dad, but I still have to do this assignment. So anyways, but now I program all the time. It just took me a while to get there. I just couldn't wrap my head around it knowing functions already. Now I get it, but like, how does it know? How does it know to do that? I couldn't get there. So there's hope. If you feel that way, there's hope. One of the things that we had to do was make a program that generates Pascal's triangle. So what does it do? It starts at 1 here, and then it goes to 1 and 1, right? Just thinking about those coefficients. And then it goes to 1, and then the sum of the previous 2, 1 plus 1 is 2, and then 1 again, right? Just 1's on the outside, like I said, those extreme combinations. 3 is the sum of 1 and 2. 3 is the sum of 2 and 1, right? And next line, 4 is the sum of 1 and 3. 6 is the sum of 3 and 3. 4 is the sum of 3 and 1, right? And so that's how this triangle, even if you didn't realize they were choose functions, right? You could develop this triangle and do it relatively quickly, right? Now we have the choose function, so we don't need to think about that, but you can just check, right? 5, 1 and 4, 10, 4 and 6, 10, 6 and 4, right? Surely it doesn't keep going like that. It does. It's crazy. Have you guys had to program Pascal's triangle? No? Special kind of pain that they only put us through, I guess.
They probably do something like that the semester.
Yeah, maybe. I was up at UBCO and yeah. I think the prof that I had thought that, well, especially me, thought I knew more than I actually did. It's a little overly confident in my abilities. But I got through it. Okay. Now, what we just found, we can generalize it and say, okay, if I have x plus y to the power of n, I can rewrite that as a summation, right? First one, second one, third one, right? I'm working my way through. And so from k equals 0 to n, right? I have a power of n here, so that's where that comes from. And we start by choosing 0 and then move our way up to n choose n, right? One thing I want you to pay attention to here, because it'll get you, is this is x plus y, right? This is going to be important to keep track of because we're obviously not just going to work with x plus y. We might have something like 5x minus 4y, to the power of 6, right? What if we wanted to expand that? Okay, so then I have to rewrite this in terms of something plus something, right? Where the first something A is X and something B is Y. Okay, so you have to be consistent that way, but it has to be in terms of the addition, okay? But then we're off to the races, says I. The sum of n choose k as you move through your k's of x to the power of n minus k, right? We started with the highest possible power of x, which is n minus 0, right? So 5 in our case, in the previous example, 5 minus 0, and to the power, or y to the power of k, which for the first iteration is 0, right? And then we moved through, and what's that? Is it stop photography, or what is it when you take pictures and you make a video? What's that called? Stop motion, yeah. That would make a great stop motion video. Cute. Okay. Let's do this one, but don't look ahead. Let's just do x minus y to the power of 4. Now what I'm going to do here is I'm going to scroll down here and say expand x minus y, what was it, to the power of 4? Eek. Yeah. Okay. And let's just remind ourselves what that binomial theorem looks like. Copy. Okay, so using this, I have to rewrite this inside as x plus y. Okay, I think the easiest way to do that is going to be eraser again. X plus negative y to the power of 4. Right. Subtraction is just a special form of addition, right? It's just adding negative numbers. So far, so good. What do I see here? I see that n is equal to 4. Right. That's a good place to start. So then wherever I see a y, I'm going to write negative y because that's what I have for my y, right? These are just placeholders, and x stays x. Okay. First, I'm going to write out this summation, and then I'll expand it. Okay. So this is going to be the sum from k equals 0 to n, which is 4, right? Of 4 choose k, where k changes with each iteration, right? Of x to the 4 minus k times y to the power of k. We've worked with this before, right? Where we had summations, and for those sums, we just change the k now, right? X and y are going to just stay variables because we don't have values for x and y, but that's what we wanted, right? We want to expand this thing. All right, here we go. Starting at k equals 0, we have 4 choose 0, x to the power of 4 minus 0 times y to the power of 0. right? I'll just emphasize here, let's pick a color. Running out of colors here. This is when k is equal to 0. Then we can move on, right? We want the sum, so we're adding all these up. Plus, now k is 1, so 4 choose 1 of x to the power of 4 minus 1 y to the power of 1. Wow, hey, how come nobody said anything? Wowzers. What did I do? What did I do? But that means here and here. I feel like I even said something. I always forget these, or maybe just in my head. I was saying, don't forget the negative. And then I forget the negative. Okay, I won't forget anymore. I'm gonna try not to forget anymore. Oops, not plus. Moving on, 4 choose 2, x to the power of 4 minus 2, y to the power, negative y to the power of 2. Whenever I don't have space here, right, I always bump it in just a little bit. The only reason I mention that is because it makes it more readable, right? And so when I'm marking your test, for example, then I have to read your work. So I would love it if you also kind of bumped in your work if you had to continue on the next line. Just bump it in a little bit. Plus 4 choose 3, x to the power of 4 minus 3, negative y to the power of 3. That's k equals 3. We're so close. Plus 4 choose 4, x to the 4 minus 4, negative y to the power of 4. These choose functions are just going to reduce to numbers, right? So let's see here. Well, we know 4 choose 0 is 1. And x to the power of 4 minus 0 is x to the power of 4. And then anything to the power of 0 is just 1. You're welcome to just write it nicely right away. That's fine. What I'm doing, I'm just trying to keep it the way it is. So I'll have one extra line of work that you don't have to show. I know, but it's good to see it though. All right. Plus 4 choose 1. How about I just change this is 4 and I'll do the others as well. 4 choose 2, 4 choose 3, 4 6 4, which we could have grabbed from that Pascal's triangle, right? So you can confirm your choose functions. But so now I have 4 times x to the power of 4 minus 1, which is 3, and then negative y to the power of 1 is just negative y. 4 choose 2 we found was 6 times x to the power of 2, negative y to the power of 2, plus 4 choose 3 is 4, x to the power of 1, negative y to the power of 3 plus 1, right? 4 choose 4 is 1 times x to the power of 0, which I guess I rewrote immediately as 1 here, a little inconsistent. I'll do that again. And then negative y to the power of 4. Woo! Now I'm going to simplify. Luckily, the powers of x are already in decreasing order, right? So I'm not going to rearrange or anything. Usually we rewrite polynomials in decreasing powers of x or y, but then I'd have to rework it, and I don't want to do that. So I have x to the power of 4 minus, right, because I have that negative y, but that negative is just multiplying by negative 1, which I'm going to bring over here. So I have minus 4x to the 3y. Negative y squared, I guess, is kind of cheeky, because negative y squared is just going to be positive y squared. Why? This is negative 1, and maybe I should write it down here, sorry. 6x squared, and then I have negative 1 squared times y squared. But negative 1 squared is just 1, right? Because I'm technically multiplying inside these brackets, so I'm allowed to bring this square onto each of the terms. I'm only allowed to do that if I'm multiplying or dividing, right? That's why we're expanding this thing in the first place. But negative 1 squared is just 1, which means that 1 times 6 is just 6. I'll leave it as is. Okay, fine. 2 extra lines of work. But it's good to keep track of it. 4 times x to the power of 1 is just 4x, but then negative y to the power of 3. Now, negative values to an odd power retains the negative. Okay, and so I'll do the same thing since I'm rewriting it anyways, but 4x, and then I have negative 1 to the 3, y to the 3. So close to fitting it on one line. Plus 1 times 1, that's great. And then negative 1 to the power of 4 times y to the power of 4. Negative 1 squared is 1. Negative 1 to the power of 3 is negative 1. And negative 1 to the power of 4 is 1. So just be careful. Now, I feel like I'm ready. X to the 4 minus 4x to the 3y plus 6x squared y squared minus 4xy to the 3 plus y to the 4. Really hope I did that right. Looks longer than what they had. Oh, that's because they're cheating. We did it all. I guess the question is this quicker than just expanding it? X minus 1 times x minus 1 times x minus 1, or x minus 1. X minus y times x minus y times x minus y times x minus y. It would be. You're welcome to try it, right? Or you could, if you're glutton for punishment, x minus y times x minus y times x minus y times x minus y. Could expand those, being careful, canceling, right? Collecting like terms, and then you would end up here. Why was the answer here so short? I didn't read it even. Find the third term in the expansion. So let's have a look at the third term. One, two, three. We did it. 6x squared y squared. What's another way that you could think about just the third term? Well, if it's that simple, that's boring, right? The third term is when k equals 2. Remember, we're starting the index at 0, right? So remember that 0 term first. Okay. So the third term index starts at k equals 0, right? That's important to remember. So then the third term is just going to be 1 less than the one that you want, right? So in that case, k is equal to 2. If k is equal to 2, and we know that n is equal to 4, right? That term is going to be 4 choose 2 of x to the power of n minus k times y, which in this case is negative y to the power of k, right? And that's how we can get to 6x squared y squared. Any questions about that? Kind of tricky. Right? But as long as you don't get tripped up like I did, you're safe. Okay. What if you have to expand something like 3x minus 2 to the power of 3, right? The most important part is taking this and extracting the information that you need, right? N is equal to 3. That's important, right? Because the power is 3. Let me zoom in here. X is 3x, but y is going to be, so plus y. Remember that general setup has to be in the form of x plus y and then to the power of n. So then y is going to be -2, right? There's no variable y, but that's okay. Just letting it be -2. Once we have that, it's really just a matter of being very, very careful, plugging in values. Don't forget the negative, like me. Then we can set up the summation, the sum from k equals 0 to 3 of 3 choose k, 3x to the power of n minus k times -2 to the power of k. It's actually nicer because -2 is just a number. So when you take it to the power of k, you'll be able to find a number right away. And so you can use Pascal's triangle or the choose function on your calculator. Either way, you're going to be able to find that 3 choose 0 is 1. 3 choose 1 is probably 3. 3 choose 2, again, 3. 3 choose 3 is 1. Where did I get those from? Well, besides kind of knowing what they are, I'm looking at or in my mind, I'm thinking about Pascal's triangle. When n equals 3, I have 1, 3, 3, 1. Right? But I think you should confirm it with the choose function on your calculator as well. Once you have those, right? 3 choose 0 is 1 times 3 to the power of 3 is what? 18? No. 3 to the power of 3 is 9 times 3, 27. Thank you. The answer is right there. I don't know why what is it, guys? Because -2 to the power of 0 is just 1. That's why. Thank you. Same deal. 3 choose 1 is 3 times 3 squared. 27 again. 3 times 9 times -2, -54. Phew. And so on and so forth. And then you can simplify it until you just have x's and y's. And in this case, there are only x's. Right? Making sure, just to check your work, right? When you're expanding this thing, you're going to have a power of x starting at 3 and decreasing by 1, right? If you don't, you've missed something. Okay. Nice. And that's the end of the new material. Maybe I'll draw a little. We'll draw a line that we did it on the next page. There. Kind of a you had to be there moment, I guess. Skip ahead. Okay. What I was thinking we would do is work through these exercises because we haven't had time to, we didn't do them on Monday, obviously, we just finished them. We did do some of these. The one I want to focus on maybe is this lattice one, if that's of interest, maybe. I found it to be, well, yeah, once I saw it, I'm okay with it, but I want you to be okay with it too. The other ones I feel like are relatively reasonable. You just have to think about it a little bit. And, whoa, come on. And I've already posted the solutions, obviously. But it was hard to communicate how I went about it. Okay. So at first, I was just overwhelmed by the question. Happens to me too. It's all right. But you have to embrace that. The image below shows a 6x6 grid and an example of a lattice path that could be taken from 0, 0 to 6, 6. So from here at 0, 0 to 6, 6. So here is the path that was taken, right, up, right, up, up, right, 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 up, 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 up. And then I got there. By traveling along grid lines, going only to the right and up. So we assume that those are the constraints on our paths as well. How many different lattice paths are there of this type? Uh-oh. And then after we answer that, we want to generalize the case of lattice paths from 0, 0 to mn, not just 6, 6. Okay. What could you do? If it was just a question about going to 6, 6, you could brute force it. There's a lot though. So I'm going to say no, thank you. Okay. But you could figure out how many ways I can get there. But as you start to map out the different paths that you could take, what's another route that I could take? I could go up 6, right 6. That's a path, right? I could go right 2, up 2, right 2, up 2, right 2, up 2. That's a path. What are they all going to have in common? And I'll be honest, I had to map out a couple more to convince myself that, okay, well, regardless, it seems to me that I need to obviously move to the right 6 times and up 6 times. That's not, I don't know why that's not obvious to me, but it wasn't, and that's okay. I got there eventually, right? How do I get to 6, 6? Well, I have to move over to the right 6 and up 6. Fair, yeah. So let's jot that down first. Oy. Any path must have 6 R's and 6 U's. Right? I have to move to the right 6 and up 6, which means that I'm making a total of 12 moves. Right? I can think of this as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? Where I have 2 options for each until I run out of R's or U's, right? Where I have to split these 6 R's and U's. Oh, should probably do the whole 6 R's and U's. So that's hard to think about because you start off with 2 options until you've run out of options. I mean, it still works, but let's think about it in terms of a choose function, right? If you focus on just one of the R's or one of the U's, because there's only 2 options, right? Then what can I do? I can say, okay, well, out of the 12 moves, how many ways can I rearrange 6 R's, right? Which is the same as, right, on the other side of those 12 are the U's, right? And so here, how many combinations, or maybe I'll say rearrangements of 6 R's in 12 moves, where I want to emphasize that this implies 6 U's, right, in 12 moves. And maybe I should extend this technically. Right. Twelve, choose 6. I'll just recycle this. 12, comma 6. I get 924. Question is that what I got in the solutions? Check against my own solutions. probably not the best idea, but it is. Okay. Phew. Kind of a complicated problem that boils down into not very much math, right? But it took a lot of thinking to get to here, right? Where, okay, well, 6 to the rights and 12 moves, right? 6 ups are implied, that kind of thing. And so relatively easy answer, but a lot of work to get there. What if you have to expand this, right? From 0, 0 all the way to mn. Okay, so now what if we moved, oops, from 0, 0 to mn? Now that we've tackled it with a concrete number, right, 6, 6, right, I can replace that with m is 6, n is 6, right, and just kind of convince myself that I'm doing the same thing, right? Here, I have to move to the right m, so this means that there are m r's and n u's, right? Just in general, I have to move to the right m units and up n units. For a total of how many moves? M plus n, right, which equals m plus n total moves. Now, it doesn't matter if you use m plus n choose m or m plus n choose n. Should have used letters that sound different. B and D, B and P, they all sound the same. Right? It doesn't matter because one implies the other in a total of m plus n moves. So what we can say is we could say there are m plus n moves. How many ways can I rearrange the m? Or if I wanted to, I could say, well, that's the same as doing m plus n choose n, right? Since here I'm rearranging r's, which implies u's, and here I'm rearranging u's, which implies also rearranging the r's, right? The remainder are going to be the r's. So it doesn't actually matter which one, they're both going to give you the same answer because of Pascal's triangle. Nice. So either one of these answers is correct. Whew. Any questions about that one? Okay, I did have one more in mind, but does anyone have any that they want to go through? I do have one more question that I thought we should go through together. Oh, all right, let's do it. I know. Maybe I shouldn't have said that because now you're all curious. Which one is it? Which one's so important? It's the very last one in this section, which usually means it's the hardest, right? But I'll give you some time to work on it. in case you haven't, and I don't think that you have because we didn't cover this material yet, but a class of 12 computer science students are to be divided into 3 groups of 3, 4, and 5 students to work on a project. How many ways can this be done if every student is to be in exactly one group? Okay. So I'll let you work on that and see what you get to. What's interesting is, maybe I shouldn't be giving it away. Try it with, so here, the starting point would be to build your group of 3, right? Then your group of 4, then your group of 5. What I want to show you is, I'll show you by making the first group of 5, then the group of 4, then the group of 3, or some combination of that, and we end up at the same value. It's crazy. So give it a go, see what happens. But we'll work through it in a little bit. Is this when I pause the recording, I think? I never do, I never remember. Play. Okay, nice. All right, so we have a total of 12 students that we're going to be rearranging, and let's start by making the group of 3. Doesn't matter, there's no order here. You're either in group 3 or you're in this group of 3, or you're not in this group of 3, right? So when you think of it that way, then it's a combination. And what we have is we have 12, choose 3. So from 12 students, how many ways can I select 3 of those students? 12, choose 3. I'll use my, oops. 220. So I have 220 ways that I can choose 3 students out of 12. Now my group of 4. Cuidado. I've removed 3 of them, right? So now I don't have 12 to choose from. I have 12 minus 3 to choose from. So I have 9, right? I have 12 minus 3 equals 9 students to choose from. Right. Should have left myself more space there, but that's okay. And from those 9, I'm going to choose 4. 9, choose 4. Just use a calculator. We could use the factorials if you wanted, but I just use a calculator. 126. It's good to know that you could. Convince yourself that you could. And then finally, the group of 5. Now, again, I don't have 9 students. Now I have 9 minus 4 students, which puts me at 5. There's only one way that I can arrange them. Right. So I have to have a group of 3 and 4 and 5. So I have to multiply this out. Oops. So group of 3 and 5, or sorry, and 4 and 5. That's a weird way of writing it, but I get 220 times 126 times 1 times 27, 720. Doesn't look very nice. So 27,720 ways that I can make these groupings. Like I said, what if we flipped it, right? What if I made my group of 5 first, right? Because that was my initial, well, which order are we making these groups in? And then I took a step back and I thought, all right, maybe it doesn't matter. Let's reorder the way we form the groups. Right, group of 5 first. Group of 4 and group of 3. And hopefully after this, you'll be convinced that, okay, fine, doesn't matter. The group of 5, and let's use this color, is from 12 now, right? So we have 12, choose 5. Let's do 12, choose 5. $7.92. $12 minus 5 is what, 7? Often it's 7. No guarantees. 7, choose 4, right? So you apply the same theory, right? It's just different groupings. 7, choose 4. It's 35. And finally, 3, choose 3. There's only one way to do that. So 792 times 35. $27,720. What? I'll just do this. 792 times 35 times 1 is 27,720, which is the same, right? Which if you think about it, it makes sense, but it's not obvious. It's not mathematically obvious right away. Okay. Any questions about that one in particular? Let's start there. Yeah. Any other questions? Okay. Any questions from the other sections that you want me to go through? Put me on the spot. Do you want to go home? Me too. But if you have any questions, let me know. I'm happy to stick around, but I think that you deserve the weekend that's yours now. All right, I'll stop this recording. Like I said, I'll hang around if you have any questions, but that is it.